Hello, today we're continuing in the A-Level Physics Revision series, and in the next two videos we're going to be looking at the subject of fields, and in particular gravitational and electric fields. This video is looking at gravitational fields. By fields I do not mean the things in the country that cows graze in. A field is something which has a value at all points in space. For example, in a room you might take a thermometer and measure the temperature at every single point in the room. Now, it's unlikely that the temperature will be the same at every point. Near the window it might be a little cooler, near the fire or the radiator it might be a little warmer, but there will be a value at every point in the room, and that is the temperature field. And what does a temperature field do? Well, it just sits there. It doesn't do anything until you put something in the field with which that field might be able to interact. For example, some ice in the room will melt, and the temperature field will have an impact on that. So a field is essentially the capability to do something, but you don't do anything until you put something in the field with which it will interact. Now, in respect of a gravitational field, here's a gravitational field, that will sit there until you put a mass in that field. And if you put a mass in the field will cause the mass to accelerate. Similarly, when we get to an electric field, if we have an electric field, you'll find that that will sit there unless you put a charge in the field. And if you put a charge in the field, that charge will be accelerated by the field. So the field is essentially a capability to do something if something with which that field interacts is placed in the field. Now, it was Newton who discovered that all masses attract one another, and the force of attraction between two masses is equal to minus, I'll tell you why it's minus in a moment, g, which is called the gravitational constant, times the mass of the first object times the mass of the second object divided by r squared, where r is the distance between the two objects. And this makes it what's called an inverse square law. In other words, as the distance doubles, the force goes down fourfold, r squared. Why is it minus? Because the force operates in the opposite distance, in the opposite way to the distance. So, for example, if you're standing on Earth and you're above the Earth by a distance of r, then r is measured upwards, but the force will act downwards, and that's the reason for this minus term here. It's important to note that if we're talking about the Earth or the Sun or any large body, r is the distance from the centre of the Sun, not the surface. The centre of the Earth, not the surface of the Earth. Don't make that mistake. R is always from the centre. The value of g is 6.67 times 10 to the minus 11 Newton metre squared per kilogram squared. Which might sound like a mouthful, but when you think about it, the constant has got to balance the two sides of the equation. Force is measured in newtons, mass is measured in kilograms, and since there are two of them, that will be the kilogram squared. And r is measured in metres, and since it's squared, there will be metres squared. So for this to be dimensionally consistent, g has to be in these units. And this force, as we shall see, is the force that keeps the moon going round the Earth and keeps the Earth going round the Sun. Now let's consider what happens if you're standing on the surface of the Earth. The Earth has a radius, r, and not to scale, here are you standing on the surface of the Earth. You have a mass, which we're going to call little m. The Earth has a mass, which we're going to call capital M. And so it will be true from this formula that the force between you and the Earth will equal minus g times your mass, little m, times the mass of the Earth, big M, divided by r squared, because you remember I said you have to measure it from the centre of the Earth, and that means the distance is the radius of the Earth. Now, on the surface of the Earth, G is a gravitational constant, that doesn't change. M is the mass of the Earth, that doesn't change. And r squared, the distance from the centre of the Earth, doesn't change if you remain on the surface. So the only thing that changes is if instead of you being on the surface of the Earth, we're talking about me. So the value of minus gm over r squared is always a constant for anything or anyone on the surface of the Earth. The only thing that changes is their mass. And this value, if you work it out, comes to 9.81 meters per second squared. And that we call little g. It's the value of gravity on the surface of the Earth, or not too far above it. For the first 100 meters or so, this is a very good approximation to the value of the gravitational attraction. So using this formula and replacing minus gm over r squared by little g, you get that F is equal to m times little g. You can put a minus sign, but now there's no radius term, so actually we can just say the force, which will of course act downwards, is equal to the mass of the object on the Earth times g. And that has a very close similarity to Newton's second law, F equals ma. What we're really saying is that the acceleration that you will experience is equal to the value of g. Of course, when you're on the surface of the Earth, you won't go through it because the Earth is strong enough to stop you doing that. But if you're a few meters above the Earth, then you will accelerate towards the surface with the acceleration g, 9.81 meters per second squared. Now this is the position only when you are close to the Earth. If you are observing the Earth from outer space, then the field lines of gravity, the gravitational field, will move in, and they always of course go towards the Earth, radially from all directions. But if you are standing on the surface of the Earth, then a very good approximation is that gravity just acts straight down. Now, since the force of the gravitational field is acting towards the Earth, if you want to move something in the opposite direction, you will have to do work. And in doing that work, you will give the object potential energy. That means energy to fall back down again. And the potential energy, which we describe as EP, the potential energy, gravitational potential energy, is equal to minus g, the gravitational constant, times the mass of the Earth, or one object, multiplied by the mass of the object that you're moving away from the Earth, divided by r. And in that respect, it only differs from the formula for the force. Force has r squared. The potential energy simply has r. That's the potential energy. There is another thing which is slightly different called the gravitational potential. And that's what I was talking about, the capability of the field. And this is the capability of moving a unit mass. So if that little m there were a unit mass, then the gravitational potential, which we call V, is equal to EP divided by m, which is minus gm over r. That's the capability of moving a unit mass. Gravitational forces act between all masses. They even act between two people. But they are so small because the masses are so small that you don't notice them, you don't find yourself being pulled to somebody else. But if at least the mass of one body is massive, then there is a very strong pull, and that can cause things to orbit. So let's consider here the Earth. And let's suppose that we've got a body, this could be a spacecraft, could even be the moon, that is orbiting the Earth. It's supposed to join up there. And so here is the body, and it is orbiting with a speed v. Of course, the velocity will constantly change because it's constantly changing direction. And it is at a distance r. And r, you remember, has to be measured from the centre of the Earth. Now, if the Earth has a mass, capital M, and the body, whether it be a rocket or spacecraft or the moon has a mass little m, then we know that the force between those two bodies will equal minus g capital M little m over r squared. That's the force that is acting between this body and this body. But if that body is going in orbit around the Earth, then there is a centripetal force that is keeping that body in orbit, and that centripetal force equals mv squared over r. And that force must be being provided by that force, so those two forces are equal. Now, before we proceed to look at the consequences of these two equations, it might just be helpful if I demonstrate why the centripetal force is mv squared over r, since that's something that people don't always know or understand. Let's take a body that is in orbit, or indeed anything going round in a circle, and that circle has a radius r, and the body is travelling at velocity or speed v, but its velocity is constantly changing. It's staying at v, but it's just changing direction. It's travelling in a time dt, and by dt it's got to there, and it travels through an angle that we will call d theta. Now, what can we say? Let's call this distance around the arc of the circle dx. Then d theta, if it is measured in radians, is equal to dx divided by r, because that is the definition of a radian. A radian is the arc length divided by the radius. But the distance dx that it travels round this arc is simply equal to the speed times the time. Distance is always speed times time. Speed is v, time is delta t, so dx is v dt. Now let's look to see how the velocity is changing. We need to know what its acceleration is, because although the speed isn't changing, the direction is, and so there is an acceleration. Well, the velocity at this point is in that direction. The velocity at this point is tangential to the radius, which means it is in this direction. And so we can do the usual trick with vectors. We can say, draw a diagram, this is length v, this is length v, that distance there I'm going to call ds, and that angle is d theta. It's the same angle as that angle there. You can do that just by geometry. And so now we can say that ds almost is equal to v, sorry, I've got that wrong. ds divided by v equals d theta. Not quite. What we're really doing is imagining that this is a circle of radius v. And ds is not quite the arc length. The arc length would be an arc. So it's almost ds divided by v is d theta, but not quite. However, if d theta is very small, then the arc length is pretty much equal to the length of the straight line. And what's the significance of the length of the straight line? Well, the length of the straight line is the change in velocity. Because if you want to know the difference between two velocities, you put them tail to tail, and then that line is the distance. So ds is really dv. It's the change in velocity. So now we can say that dv over v is equal to d theta for small angles. As long as d theta is small, then dv is the straight line is virtually the same as the arc length. So a brief recap: because the velocity is the same, we can imagine these 2 points as being on the surface of a circle of radius v. If that were the case, then the arc length between these 2 points divided by v would equal d theta. What we actually want is the straight line distance between those 2 points. But if d theta is very small, then the arc length and the straight line are going to be broadly the same. And so this is a reasonable approximation for small angles. Well, now we can equate d theta there to d theta there, which means that we say that dv by v, or dv divided by v, which is d theta, is equal to v dt over r, which also equals d theta. And this means that if we bring v up here, we get v squared divided by r, bring the dt down here, equals dv by dt. But what is dv by dt? Velocity divided by time is acceleration. And so the acceleration is equal to v squared over r. And if you want the force, well, the force by Newton's second law is mass times acceleration, and that is mass times v squared over r. And that's why the centripetal force is mv squared over r. Okay, after that little detour, we can now go back and look at the significance of the gravitational force being supplied, or being the cause of, the centripetal force. And if that's the case, we can say that this force equals that force. So let's write those down. Actually, strictly, of course, this force should be minus as well, since the force acts inwards, whereas r is measured outwards. So they're both minus, which means you can lose the minuses when you equate them, and you can say that gmm divided by r squared, which is the gravitational force, is equal to mv squared over r, which is the centripetal force. And that means that v squared equals gm little m over r squared, and now you have to bring r over m. The m's cancel, one of the r's cancel, and you get v squared is gm over r, which means that v is equal to the square root of g capital M over r. So the velocity of an orbiting body is equal to g, the gravitational constant, times mass, the mass of the Earth if that's what we're thinking about, times r, which is the distance from the centre of the Earth. How long does it take that orbiting body to complete one complete orbit? Well, that time is called capital T, and time will be the distance divided by the speed. What is the distance of one orbit? Well, it's the circumference of the circle, 2 pi r, where r is the distance from the centre of the Earth to the position where the orbiting body is, divided by the speed, which is v. And that equals 2 pi r divided by v. Well, v is square root of gm over r. So if you divide by v, that becomes the square root of r over gm. And if you square 2 pi r, you get 4 pi squared r squared. That can now go inside the square root. So we're squaring 2 pi r to get 4 pi squared r squared times r over gm. And that gives you that the time to complete the orbit is equal to the square root of 4 pi squared r cubed divided by gm. That is the time to complete the orbit. And it's started to get sunny, so I hope that it's not being too much of a problem seeing the words on the screen. It is terrible to do so, but I have blotted out the sun. There is something called a geosynchronous orbit. If you take the Earth, you can have a satellite that takes precisely 24 hours to do an orbit. That is to say that it spins, or it does one complete orbit, in the same time as the Earth spins on its own axis. And that means it appears to be stationary. If you are on the Earth and the satellite is overhead, then as the Earth spins in 24 hours and the satellite spins in 24 hours, the satellite will always be directly above you. And that's necessary if, for example, you want a satellite to beam you television pictures. It's no use if the satellite moves out of position, because then the dish aerial won't be able to pick it up. So what we want to know is, how far above the Earth does a satellite have to be if it is going to orbit the Earth in once every 24 hours? Well, we know that by definition t must equal 24 hours, and that will have to be converted into seconds. We also know, because we've just calculated it, that the period is equal to the square root of 4 pi squared r cubed divided by gm. This means that t squared, we're just squaring on both sides, is 4 pi squared r cubed over gm. And now we want to rearrange that for r cubed. We want to find out what r is, because we want to know how far from the centre of the Earth, remember, from the centre of the Earth, that satellite has to be. Well, r cubed is going to be t squared gm divided by 4 pi squared. And that means that r is going to be the cube root now of t squared gm divided by 4 pi squared. Now t, we know, has to be 24 hours, but that has to be calculated in seconds, so it's 24 times 60 times 60 seconds. G is the gravitational constant, we know that. M is the mass of the Earth, if that's what we want to orbit. And 4 pi squared, of course, is well known. And if you put all those numbers in, you will find that r, the distance from the centre of the Earth, is 4.23 times 10 to the 4 kilometres. But that's from the centre of the Earth. How far above the Earth does it have to be? Well, the radius of the Earth is very approximately 6.4 times 10 to the 3 kilometres, about 6,400 kilometres. So if you want to know how far above the surface of the Earth, then you have to take that distance minus the radius of the Earth. And if you do that, then you find that the height above the surface of the Earth that the satellite has to be is 35,900 kilometres, which is very roughly 22,000 miles. So a geosynchronous satellite, that is one that will stay above your head for the whole 24 hours, has to orbit at about 22,000 miles above the Earth. A man called Kepler lived just before Newton, and he made 3 discoveries about the way planets orbit around the Sun. Most of us think planets orbit in a circle. In fact, Kepler found that they move in an ellipse. An ellipse is a kind of squashed circle, although in fact the circle of the planets round the Sun is almost a circle, and a circle very often will nicely describe it and you get pretty accurate results. But strictly it's just a slightly squashed circle, an ellipse. Kepler also found that the planet, if this is the Sun and this is a planet, say the Earth, the planet sweeps out equal areas in equal time. So if the planet goes from there to there in a time, let's say t seconds, and then from there to there in a further time t seconds, so it takes 2 seconds from there to there and t seconds from there to there, then what Kepler found was that that area is equal to that area. The planet sweeps out equal areas in equal time. And the third thing that Kepler noticed was that if you take the period of the planet as t, then t squared was proportional to the distance of that planet from the Sun cubed. The time taken to do a complete revolution, one orbit, squared, was proportional to the distance from the Sun cubed. And we now know precisely why that is, because that's what we worked out up here, that an orbiting spacecraft, rocket, satellite, whatever, the time squared is proportional to the radius cubed, because for any given object like the Earth, 4 pi squared over gm are all constants. So when Kepler deduced that, he was on the way to identifying what Newton subsequently formulated. We can now think about escape velocities. Let's suppose we want to get away from the Earth, away from the Earth's gravitational field, which is pushing us downwards. And we want to escape so that we're no longer attracted by the gravitational field. How fast do we have to go? Well, let's call that escape velocity v. And that means we will have an energy, a kinetic energy, of a half mv squared. Now that has got to be at least as great as the potential energy in the gravitational field that would otherwise cause us to come back. And the potential energy is minus gm, where m is the mass of the Earth, times m, which is the mass of the rocket or whatever it is you're trying to get out, divided by r, where r is the distance from the surface of the Earth, because that's where we're starting, and the centre of the Earth. Those two things have to be at least equal. And that means that the velocity is going to be, or the velocity squared, is equal to minus 2gmm divided by mr. And the masses cancel. And now you get that the velocity squared is, we can forget about the minus sign because we know which direction it's going. It's got to go upwards. So the velocity now is, taking the masses out, 2gm over r. And if you work that out, substituting the gravitational constant, the mass of the Earth and the radius of the Earth, you find that for the Earth, the escape velocity is approximately 11 kilometers per second, which is very roughly 7 miles per second. Now you might observe that when a rocket is launched from one of the main rocket launch places, it doesn't seem to go upwards at a rate of 7 miles a second. And the reason for that is it doesn't have to, because it's got an engine. And as long as you've got an engine providing a constant force, then you can go up much slower, because that engine will continue to give you thrust to overcome the potential energy that would tend to pull you back down again. What this velocity says is that if you could give an object a velocity of 11 kilometers per second, then without any further engines, it would go into outer space and out of the Earth's gravitational pull. So if you could get, say, a cricket ball or a tennis ball and whack it with a bat or a racket, and if you could give it a speed of 11 kilometers per second, 7 miles per second, then you could get it into outer space. Now, 7 miles per second, in terms of miles per hour, you have to multiply 7 by 3,600, which I think comes to something like 25,000 miles an hour. So you would have to hit your tennis ball at 25,000 miles an hour in order for it to go into outer space and escape the Earth's gravitational field. And since the best tennis players in the world serve an average of 160 miles an hour, they've got some way to go before those tennis balls go out into orbit. Hello, today we're continuing in the A-Level Physics Revision series, and in the next 2 videos we're going to be looking at the subject of fields, and in particular gravitational and electric fields. This video is looking at gravitational fields. By fields I do not mean the things in the country that cows graze in. A field is something which has a value at all points in space. For example, in a room you might take a thermometer and measure the temperature at every single point in the room. Now, it's unlikely that the temperature will be the same at every point. Near the window it might be a little cooler, near the fire it might, or the radiator, it might be a little warmer, but there will be a value. Talking about the Earth or the Sun or any large body, r is the distance from the centre of the Sun, not the surface. The centre of the Earth, not the surface of the Earth. Don't make that mistake. R is always from the centre. The value of G is 6.67 times 10 to the minus 11 Newton metre squared per kilogram squared. Which might sound like a mouthful, but when you think about it, the constant has got to balance the two sides of the equation. Force is measured in newtons, mass is measured in kilograms, and since there are 2 of them, that will be the kilogram squared. And r is measured in metres, and since it's squared, there will be metres squared. So the mass of the second object divided by r squared, where r is the distance between the two objects. And this makes it what's called an inverse square law. In other words, as the distance doubles, the force goes down fourfold, r squared. Why is it minus? Because the force operates in the opposite distance, in the opposite way to the distance. So for example, if you're standing on Earth and you're above the Earth by a distance of r, then r is measured upwards, but the force will act downwards, and that's the reason for this minus term here. It's important to note that if we value at every point in the room, and that is the temperature field. And what does a temperature field do? Well, it just sits there. It doesn't do anything until you put something in the field with which that field might be able to interact. For example, some ice in the room will melt, and the temperature field will have an impact on that. So a field is essentially the capability to do something, but you don't do anything until you put something in the field with which it will interact. Now, in respect of a gravitational field, here's a gravitational field, that will sit there until you put a mass in that field. And if you put a mass in the field will cause the mass to accelerate. Similarly, when we get to an electric field, if we have an electric field, you'll find that that will sit there unless you put a charge in the field. And if you put a charge in the field, that charge will be accelerated by the field. So the field is essentially a capability to do something if something with which that field interacts is placed in the field. Now, it was Newton who discovered that all masses attract one another, and the force of attraction between two masses is equal to minus, I'll tell you why it's minus in a moment, g, which is called the gravitational constant, times the mass of the first object times